Hi, my name is Russ. This is the fifth video in a series of videos that's being constructed from the topics as found in NFPA 921. NFPA 921 is the document for fire and explosive investigations. It's a guidebook. It's pretty much the standard in industry for forensic analysis. I'm going to use that, and as with the other videos, other sources to, I guess, basically expand the information that's available from NFPA 921. Today's topic is on melting and thermal expansion in fire forensics and how those tools can be used to identify fire origins and also basically reconstruct a fire after the fact. Keeping in mind that fire damage, it really destroys your evidence. So you have to use some unique tools to be able to reconstruct basically a compartment or the kind of a surrounding situation that existed prior to the fire. So melting and deformation of metals provides clues as to the temperature around the damage during the fire. And what that does is it helps us identify both the temperature and duration of the fire. Uh, what you'll observe is typically flashover fires. The number used is usually about 975 degrees Celsius as the delta between ambient and what the flashover conditions are, the maximum temperatures. But I want to be clear. Um, you're going to have spikes here and there that go up to 1300 degrees Celsius. You'll see that in the data that's been performed through the experiments that have been performed in reconstructing fires, compartment fires. And a lot of that has to do with the reflective nature of a compartment. So if you have a room and you have a fire, keep in mind that a fire, using Fahrenheit, the flame is 1860 degrees Fahrenheit. It's basically what the median flame temperature is for the flame tips. But when you have a reflection from multiple sources, let's say a room's on fire, you're not only going to feel the temperature of that flame, you're going to feel this heat flux from other sources that raises up that temperature. And that's the kind of situation you're going to have in a flashover. So that's why, even though you kind of have a rule of thumb of about 1,000 degrees Celsius, you can't see higher temperatures. And reconstructing a fire, you're going to use temperature in some cases in terms of deformation as well as what material melted and what didn't, and reconstructing what how that fire progressed and what it might have looked like. Here's an example that illustrates this. So I used the statement before that flame temperature is about 1860 degrees Fahrenheit. Well, the melting point of copper depends on several factors in terms of alloys, but you can usually gauge about 1960 degrees Fahrenheit. Here's an example where you have a hole in this copper pipe, this image. Now that was not due to melting of the copper, but what happened was you had molten aluminum fall on copper and it melted. And in Fahrenheit, the temperature for aluminum melting, it depends on if it's an alloy or if it's pure aluminum, but it ranges from 1,000 degrees Fahrenheit to 1,220 degrees Fahrenheit for now, pure aluminum, for instance. So if you had a drop of molten aluminum fall on copper, what happens is there's some localized alloying. And typically alloys, metal alloys, can often have an alloy melting temperature below the melting point of either of the pure substances. Take solder as an example. It's called a eutectic combination or eutectic material, a combination that results in a lower melting point. So in this case, copper can actually melt below its melting point if it's mixed with aluminum. And the reason I bring this up is one of the conspiracy theories associated with the World Trade Center towers is that it was noticed that they had liquid metals pouring out of the bottom at a certain location. And the conclusions were drawn, well, hey, you can't do that at standard temperatures. And what more than likely happened was you had an alloying event occurring where you had some aluminum mixed with copper, resulting in these metals pouring out. It could have been other materials. Clearly other materials within buildings exist. But one thing you have to understand by this, you're not going to see steel alloying and behaving like that. These are the other substances. Steel, both carbon and stainless, you're going to have a much higher melting point, and the alloying just does not result at standard structural temperatures. So if you do have alloying, or excuse me, flowing of steel, that's a telltale sign that there's something else going on that needs further investigation. It's just not a normal event. So I included various melting points here. just so you can get a feel for things. One thing to keep in mind is that plastics, so thermoplastics like nylon or polyethylene, it's going to have a range of melting temperatures. So you're going to become plastic deformation is a term used when it's something softened. So not only is it a term for material plastic, but it's also an event. It becomes plastic. I hate to use the two same terms with two different definitions, but you can actually have plastic go through a plastic range before it melts. Now, consider water, for instance. So you can have frozen water, you can have melted water. They exist at the exact same temperature. So 32 degrees Fahrenheit or 0 degrees Celsius. So they can coexist. Hence, a glass water with ice cubes in it. Same principle. That doesn't necessarily exist like that. There's not this clear defined solid melting temperature for some materials. There's a range of some materials. Thermoplastics is an example of that. And what you can see here kind of demonstrates that. So in this case, the light on the left, what that tells me, and if you look at the line of demarcation on the back wall, you can kind of tell there clearly was an upper layer, an upper smoke layer, and an upper smoke layer is let's say 1,000 degrees Celsius there in terms of plastic. Now melting, because plastic or any material has mass, and that mass it stores energy. So let's say, if you hand in hand and put your lighter underneath it, you can do that for a very short duration. That's because the mass takes time to absorb that energy. Well, the same thing can be applied in a situation where you're doing fire forensics. Not only is temperature the issue, but time of exposure is the issue. Take a look at this light fixture, though. What's interesting here, what you can note, is you may well have had an upper layer of elevated temperature. But what appears to have happened also is you had a radiant heat flux on the left side of this that resulted in a higher amount of heat transfer to the left portion of that light fixture cover. That resulted in this deformation. Also consider the light example, the outdoor light on the right side. Observing the behavior of these materials in that light suggests it had a higher heat flux from the right side. It wasn't likely, smoke temperatures in that case. It wasn't like an upper layer of smoke that created a convective heat transfer. It was more likely strictly a radiative heat transfer into that light. And you can use these as tools in identifying the location for greater intensity for where the fire may have been hotter than other locations. So glass softens at 600 degrees Celsius, melts at 1500 degrees Celsius. So once again, that range we talked about. Most thermoplastics melt at or below 260 degrees Celsius. Not always the case. There's a lot of specialized plastics that are 100 degrees more than that. Be clear, melting of materials is a tool that can be used for determining the direction of a fire. It's not necessarily going to give you, a telltale sign of an origin. So you got to apply that with multiple tools. For instance, look at these trash cans. The trash cans shown in the left side, left image. What that tells me is the fire obviously was in front of that. And, it might have been quite a ways away, depending on how big the fire was. And that kind of tool, by identifying where the melt was in plastic, for instance, and how much melt occurred, it'll help you narrow down, if you have a large fire, let's say, that surrounds plastic, it'll help you identify where the more intense fire occurred. Similarly, look at the glass patterns in the left image. If you have a series of windows, for instance, that show some softening and others don't show softening, so there's almost like a demarcation between the softened glass and the non-softened glass, that's going to help you narrow down in terms of where the hotter fire may have been. So lines of melt demarcation allows for determination of temperature in specific location. Another thing that's often mistaken is oxidation can be mistakenly interpreted as melting. So look at bed springs. They're very small. Consequently, they have a high surface area as a function of mass, which means oxidation has a greater impact on them. There's more surface area to oxidize as a function of mass because of the narrow diameter. So what happens is during fire forensics, you'll see springs that appear melted or destroyed. It's actually not melt; it's oxidation. This is something that's frequently confused, resulting in forensic investigators, arson investigators, to give false testimony, and that's somewhat dangerous. So don't assume ignitable liquids were used just because you have alloying metals, or you have springs that appear to be damaged. That this was a mistake used by some conspiracy theorists in terms of the World Trade Center, and that leads to dangerous conclusions. There may be other subtleties associated with the WTC incidents, but alloying liquids pouring out of the bottom of the structure, it's reasonable. Let's take a look at I-beams now. Bending and buckling of steel members. I mentioned before in another video that typically structural engineers use 550 degrees Celsius as the threshold for zero strength. So you're going to have buckling greater than 500 degrees Celsius material temperature. And one thing I've noticed when you do the heat transfer equations in terms of the transfer both through convective and radiative heat transfer into steel, you have a very, very fast rise time. So if you're surrounding steel by heavy black upper layer smoke from a fire, the steel actually very closely follows the temperature changes in that smoke. And the reason for that is your conductive coefficient of conduction for steel is about 45.8 watts per meter Kelvin, I think is what the units are on that. So that's roughly 50 times more than, let's say, concrete. So because, and put that in perspective, copper is like 360. It's just monstrously higher. So copper very rapidly follows the smoke layer. But in the case of steel, it's going to follow the temperature of the gas layer around it, the hot gas layer. But there's some caveats to that you need to understand. So when you look at an I-beam, you have an upper flange, a lower flange, and then a web. So it's an I-beam. It looks like an eye on the cross section. And what happens is thermal deformation is also a major factor for that smiley face look on I-beams. So what you have with an I-beam, let's say you have a girder. An I-beam's a girder, used as a girder, and you have these basically these floor beams on top of the girder. And the floor beams are applying a load to that girder. Now what happens, however you want to set this up, you could have a concrete deck on a girder or beam or whatever it may be, but you're going to have a deformation. Now a lot of people assume that's only because of the applied load. And there's definitely applicability to that conclusion. But there's one other major factor that's often overlooked. And what that is differences in thermal expansion between the bottom flange and the upper flange. Keeping in mind, let's take a 100-meter, let's use as an example, a 100-meter long I-beam. Just using these as rough numbers, you're not actually going to see that, but a 100-meter I-beam. Now, if I raise that by 1,000 degrees Fahrenheit, based on the existing coefficient of expansion for steel, I'm going to see a 1 meter expansion on that beam. So it's on the order of 10 times 10 to the minus 6 per degree Celsius. I think that's about what the coefficient is, 10 or 11. But regardless, using that example of a 100-meter beam, you're going to see a 1 meter expansion for 1,000 degree increase in temperature. Keeping in mind, 1,000 degree Celsius is typical for a flashover condition. So you don't need a lot of expansion or a long beam to move quite a bit in the event of a flashover related fire. So what happens though specifically with I-beams is if you have a deck on top of your I-beam, let's say you have a steel deck with concrete above it or basically some kind of heat sink. So that upper flange layer is touching something that has mass that could draw energy out of it. What you'll see happen is a different rate of heat transfer into the bottom flange fully exposed not only to hot gases but also to the heat flux. You'll have a different heat expansion there than you will on the top flange because you're losing energy to whatever it's in contact with. And what that does is it creates greater expansion on the bottom flange than the upper flange, and what that does is it creates a smiley face. So that's another feature of deformation. So you have the differences of thermal expansion, and you have the applied load when steel is in a plastic state that causes that deformation. So keep those things in mind. Another thing, when you're looking at analyzing buildings, consider that plaster may expand and separate from lath. That's going to be a function of temperature and duration of exposure. Another key element is pipe fittings. You can use that as a forensic tool. What you'll see happen is that pipes will heat up, that 1,000 degrees Celsius, as I mentioned, or whatever it happens to be, but it's going to heat up, and you could have permanent plastic deformation because of that heat. As it cools, then it leaves some residual deformation because the stress is applied during the heating process, and that results in loose pipe fittings. So that's another telltale sign of hotter fires. You can analyze in terms of where you're going to see pipe fittings that are loose versus not loose, and determining where things may have burned hotter. Here's an interesting example. Now, this is a decades old photograph. But what you had is a flashover in a basement location. What happened is the beam, as described earlier, heated. That beam then expanded to a point that it, knocked out the bricks in this case. So let's consider a couple things, two things really. Let's look at the World Trade Center. So you have WTC1 and WTC2. You also have WTC7. So I'm just going to take a look really quick. Let's examine World Trade Center 1 and 2 really quick to understand how that failure occurred. So just my background to explain, I'm going to combine some engineering fields here. I'm registered in fire protection engineering, professionally registered, a PE, but I'm also professionally registered in mechanical engineering. So I have a PE in that as well. So I'm kind of merging two disciplines together in discussing this. So I'm going to use a more of a mechanical engineering term, and that's an eccentric loading on a column. So if I had an eccentric column, let's say a column, and I put the force on top of that column right in the center, it really is crazy how strong that is. But if I take the exact same column and I put the force just off on the edge, it'll buckle much easier. I mean, the numbers are staggering how much easier it is to buckle that. So with the World Trade Center, it was kind of interesting. You had a building, it was 110 stories tall, WTC1 and WTC2. Each floor was an acre. It was about 207 feet wide, I believe was what the number was. And what was interesting about WTC1 and WTC2 is that you had a center column of concrete that handled your elevators, your HVAC shafts, your stairways. I think there was 3 stairways on that structure. And what was interesting about this structure is it relied on an exoskeleton of steel to support the outside. And there was this big span. So what you had in places, let's say 50, 60 feet span between that center area and the exterior. And I'm estimating, I think that was correct though. So what you had is those I-beams that connected the center concrete area to the exoskeleton. What you had is they expanded because of the intense heat. And because it expanded against that exoskeleton, it bulged a little bit. And that created that eccentric loading that resulted in it collapsing. Because it doesn't take a lot of force. When you have the eccentric load, it doesn't take a lot of force to collapse a column. And that's effectively what happened there. What's interesting, too, on the same phenomena with World Trade Center 7 is that the fire was left to burn about 8 hours. Because you lost your automatic fire suppression, and you lost any capability for manual response for fire suppression. So it burned nonstop for 8 hours, and there may have been a lot of traveling fires. In other words, no flashovers, but it would just travel. And what that did over time is even though you had a fire rated, fire protected beams, fire rating or fiber over the beams, the fire retardant on the beams. What it does is it delays heat transfer, but it doesn't prevent it. So if you expose like a 1 hour rated beam to a fire over 8 hours, you're going to basically have the same kind of effect as if it had no fire rating at all. So what happened there that's kind of interesting is because of the nature of the fire, its progression, you had these beams heat up. And what they did is they underwent some plastic deformation. And because you had combined, the heat expansion as well as plastic deformation, it may not have pushed as much on the supports for the girders. But what happened during the cooling process after that fire had moved on, and this is most likely what happened with that structure, is actually pulled those girders back. So not only do you have thermal expansion, you have thermal retraction, but it maintained its strength as it went through that retraction process, having already been deformed, and thus the retracted size was probably much less than the thermal expanded size. In any event, what happened was it probably very likely the floor beams pulled those girders off of their supports, resulting in the collapse. So it was a series of events that transpired there, but it's just kind of interesting to consider those things. How melting of various materials are used is that you can help identify temperatures in different areas. Um, Plastic and glass fixtures will show damage on the fire side, and thermal expansion can cause permanent deformation. The greater the deformation, two factors: one's temperature, time, but the other one's load. You need to consider all those things in your analysis. In any event, I hope that was helpful. I think the one keep away is if you have alloying, don't assume an ignitable liquid was used. One of my See, I've had the chance to go through the arson classes through the various fire academies and stuff. Um, and those things are typically taught by firefighters. They're not the way the whole fire program works is they basically matriculate people up from firefighters into fire chiefs into arson investigators. You rarely have scientists and engineers in that field, and that results on their forensics basically using thumb rules. And I've actually been in those classes and have had very knowledgeable firefighter arson investigations explain that if you see molted aluminum, or excuse me, molted copper, it means that ignitable liquids were used, and that's patently false. That's just false. Um, you're gonna, especially with the alloying, you can potentially see that. So it's just important to condition the information you receive with forensic facts, and that's why this series of videos was created to ensure people have that. Here are some references you could use for your further analysis. I appreciate your time. Thank you for listening, and have a good day.